Okay, we'll start to stretch the brain a little bit. As the wind blows along the earth, it encounters friction, and the friction slows the wind. And we learned in the lesson on Coriolis that when the wind slows, or in our example, the aeroplane, when the aeroplane was slowed, the actual distance it travelled was moved to the right. So what happens is as the air comes down to the surface and slows, it actually shifts to the right. And it shifts according to the nature of the ground. The rougher the ground is, the more the wind is slowed, and the further to the right it will turn. Now the graph that's shown here is greatly exaggerated. Well, sorry, it's a much bigger scale than perhaps we might be used to, because it's showing the amount of friction and the effect on the wind that we actually have. But if you look down the graph, it touches at about where I've got 6 knots shown. It sort of touches the base 0 line. But in point of fact, it flattens more and more and more until it gets down to the 1 and 2 knots and so on. And the amount it turns, the slower it gets, the more it actually turns. And I've got on this graph the standard forecast height. The Weather Bureau issues wind speeds based on a 10-metre height, which is perhaps well up on most masts for a keelboat. And you might notice that the wind speed drops dramatically as we get closer and closer to the ground. And here's what actually happens. We've got the gradient wind, and that's there's a little bit of confusion in gradient wind, because in some cases we need to, or I've only got one terminology that I'm used to, and that's gradient wind. But sometimes in an example I'll say so when it's confusing, but gradient wind means existing wind. But in this case, the gradient wind is 2,000 to 3,000 feet high in the atmosphere. But if I want to show a shift in the wind direction according to a mast, then I would call the wind at the top of the mast the local gradient wind. So sorry about that, it's a bit confusing. It shifts in general around 20-30 degrees, and this is responsible for the weather systems. Remember we said that, for example, the high rotates anti-clockwise and the wind goes outwards, crossing the isobars at 20-odd degrees. It's the same process here. Now, the terminology you have to watch in textbooks and so on, just what their frame of reference is, because some can say that the wind shifts left, but they're talking about the foot of the arrow of the new wind direction, whereas we work on the basis that we're looking at where the arrow shifts. And for our purposes, when the wind slows, the wind moves right in direction. And just think about this, in gradient wind terms, maybe 1,000 feet high and so on, the wind is a third or is a lot faster than what it is over the land. So if that wind that's up high moves down to the surface of the land, the wind at the land surface will only be a third or a half of that aloft and 2/3 of that high wind speed over the sea. Now the term for the wind moving clockwise is it veers. And if it goes anti-clockwise, that terminology is it backs. And that's another thing that gets confusing. You will often hear in a news report that a car veered across the road, but they will use veer even if the car moves left. So you might just like to remember that a little bit. Now, the stability of the atmosphere has a lot to do with the vertical motion in the atmosphere. And you remember last week we said that the stable air is often cool or dense because it tends to hug the ground and not move a lot. So if we've got a high wind and the atmosphere is cool, it's unlikely to rapidly move vertically down to reach the surface. But if we've got sunshine on the ground, and you remember the example I gave you, if you walk on the beach on a summer's day, you only have to sink your feet through the hot sand by 3 or so inches and the sand is cool. So the land actually heats very, very quickly compared to water, which takes a long time to heat, weeks and months in point of fact. Now, when that layer of warm sand, the air that's touching that sand will absorb the heat and it will expand, become lighter, and it will rise. And as it does, it mixes and causes instability. Instability meaning that there is vertical motion with the air. And the cloud formation and type are indicators. Now let's consider some clouds. When you have cumulus clouds in particular moving through the atmosphere, pardon me, the cloud is formed because there's a column of warm air rising under the cloud, which has lifted the cloud to condensation point, and the condensation point we see as a cloud. But you can't have air just going up and leaving a vacuum down below. So what actually happens is cool air from aloft. Remember, as you increase the height of the air, it becomes cooler. So the center of the cloud is going vertically up. And on the edges, away from that rising column, cold air is coming from aloft and coming down to the ground. But the air that's Pardon me. Top water. So the air that's going up has come from the ground. It's not only warming and going vertically up, but it's been friction modified so that it's a lot less speed. Whereas the air coming down from aloft is much, much faster because the aloft air is a half or 1.25 times faster. So when the air comes down on the edges, you get a gust. And if you look across this diagram, the circular motion of air going up and air coming down, wherever you get the gusts, you get an increase in speed. Wherever you get under the cloud, you get a drop in speed. Now, you can expect about a 3-knot increase on an average reasonable day. And that 3-knot increase in the gust is right alongside the vertically moving air, which is a lull, and it has a 3-knot decrease. The net effect is as you sail along and you pass under clouds, you will get changes in speed of about 6 knots, 3 in the lull, 3 in the gust. At night time, there's a lot less heating and the stability becomes more probable as the upper air doesn't get mixed down to the surface. And generally, when you get near the sea at night and the air cools down there, the air is much colder against the sea as well. And so the colder air tends to sit on the water or on the colder land, and you get much greater stability. The rougher the surface is on the land, the greater the friction and the more the wind will slow down, and the greater the direction of the wind on the land will turn. In the case of a single cloud, you get the cloud, this is a sort of a side view, you get the cloud moving forward and the same lift underneath the cloud is occurring in the air and the same downdraft on the edges of the colder air coming down is, but you get in the front, you get the speed of the actual wind plus the speed in the motion of the air. So you get this motion of the cloud moving through the atmosphere, and you get the motion here and the slowing down here because you get this circular effect occurs. And if you look, you get this pattern, vertically moving air doesn't actually have much speed over the ground. When you get to the front of this system, you get the plus of the speed plus the strength of the downdraft round the cloud, so you get a much bigger gust in the front. Now, if you can position your boat with the clouds and get the right kind of, well, the dinghy sailors are very, very good at it, but they live and breathe on clouds and what's happening underneath. And they look at this kind of pattern here and they jump from cloud to cloud to get the best out of the direction they're going. There is another kind of gust formation which happens in turbulent air where you have an inversion layer. The inversion layer is a layer of air aloft which is cold. Because it's cold, it's pressing down onto the warmer air with cloud generally, but it's not heavy enough to break through. And the turbulence there passes into the wind underneath. I've seen the effect of this, but I haven't been able to wrap my head around the gust and see the gust formation actually happen. I'll explain it nonetheless. Under the circular motion in the turbulence up under the inversion layer, you've got the wind direction and a circular motion which is copied from under the inversion layer. This upward part here can get caught in the wind direction and be accelerated. And as it gets to this part, it's moved along, and this part comes down and catches the downside of the roll in the air here. And by this mechanism, it gets bigger and bigger to make a much greater gust. As I say, I've seen the rolls aloft and I've studied it, but I haven't actually been able to make this effect yet. But the boffins very positively say it's there. Now, just looking again at the vertical wind shear graph, if you understand that, this curve keeps going down and flattens out along here. And in particular, the effect on your sails is much more pronounced as the wind speed drops. When you get up to about 15, 20 knots, the mixing in the air is so great that you can't see this formation. And a lot of the light weather stuff I'm talking about there doesn't really happen. But let's consider your mast. The difference in direction between the faster wind up at the top of the mast and down at eye level, down here. At eye level, the wind is much, much slower. And so it turns more than what the wind is at the top of the mast. And if you're going to get the maximum light weather performance out of your sails, you need to adjust your sails in order to cater for this. Some people get bits of audio tape from a cassette and tie them on the rigging or something like that so they can actually see what's happening at different levels. But woolies on the sail have the same function. And if we look at a boat sailing to windward, we've got the gradient wind, I've called it. This is local gradient wind. In other words, not at 1,000, 2,000 feet, but at the masthead height. We've got the gradient wind in this direction, but down at eye level, we've got the wind is much more veered because the air has slowed down with the friction level and turned more. If you consider a boat sailing on port tack here, the much more turned wind at the bottom of the sail is very different to what you get at the masthead. So what do? You move your jib car forward to close the top of the sail and line up with the wind. And when it's on port tack, you move the jib car back so that you open the top and close down at deck level. So if you've ever wondered how to set a sail or what you actually do, this is the theoretical application. Sufficient to say that this effect can be so great in very light winds, especially around late autumn and early winter, that you can have the deck level of the sail in line with the motion of the boat, and the top half of your sail is very, very open. The speed of the boat is making enough wind at deck level to be in line. But that's an exaggeration. That doesn't happen. It's not an exaggeration. It only happens rarely. But in autumn and so on, you have to be very conscious of this if you want to get some speed out of your boat. And one of the giveaways, if you think, or if you're wondering, your boat goes better on port tack than it does on starboard tacks, it's a dead giveaway that you've got the car settings wrong. Any questions on that? Takes a bit of wrapping your head around. Okay. Now, if we look at a Seabreeze.
Sorry, I just had a question there. Can you just repeat when you put the cars forward on port and starboard and when you put them back?
Right. The trick here is on starboard tack, the veered wind, the blue arrow here, has turned, the wind has turned a lot more than what the wind is at masthead. And you might say that we're also talking about the top half of your sail and the bottom half of your sail. So you've got two different directions to set the sails for and everything in between. It's a matter of, if you're on starboard tack, you move the car aft and sheet on to close the angle here, and then you ease the track or the sail to actually open the bottom at deck level so that you can get all parts of the sail delivering power. And on port tack, it's the other way around. You move the car aft to open the head, which is
Sorry,
here.
you said moved aft on starboard, and now you've said moved aft on port. Which is it?
No, you move aft on port. Sorry if I got that wrong. I wasn't conscious of it. The thing is that the bottom of the sail on port tack, you've got a big angle between top and the veered wind here, whereas on starboard, you've got a fine angle between here and here. And the giveaway is if the boat is sailing better on port tack. On the beach, when that hot sand is heating the air in contact with it, the hot air rises and goes aloft, and other air has to come and take the place of the air that's risen. And the coolest air that wants to hug the surface comes from the water. So we get rising air over the land, and we get cool air moving in to take its place. And the cool air that moves in here gets replaced by cool air from a greater height. And we end up with a circulation like this. The giveaway, if this effect is happening, is that the rising air reaches condensation level and we get a cloud formation there. And this is the telltale to know when you're getting a sea breeze coming in. And here's a picture of a very calm period like you get in early winter and in late autumn. The days are not very, very warm, and the temperature difference between the sea and the land is not very great. So it doesn't happen, we don't get big waves or anything like that because the sea breeze is too light. It happens on days like we had today, where you get a bit of warming in the afternoon and a very cold night. So the cold night, the air, the sea is cold. It takes quite a while before there's enough sunshine to start to warm the land and create the updraft. Now going back to the sea breeze diagram, under rising air, it's vertical motion and there is no wind under vertical motion. And similarly in downdraft, here, there is no horizontal wind. It's vertically coming down, maybe spreading out a little bit, but this is called the sink. So you've got the updraft here and you've got the sink here. No wind under the sink, no wind under the updraft. And I'll come back to that in a little bit, but the effect of the warm land and the cool sea, the breeze always commences at right angles to the shore. And the sink in this case is in the middle there because we've got heating all around the shore. We've got the sea breeze running there, the cool air coming in, and the cool air coming out to take the place of the rising air here. So it forms fairly late in the morning, and when the sun starts to go down, you know, the cooling usually starts about 3:30 or so. This effect gradually disappears. This picture here is at Williamstown, and if you look there, you can see the sea breeze cloud, the typical shape, horizontal line there, but there's no horizontal line over here. So the sea breeze is operating around there, and the sink is actually over towards Geelong a bit, Altona, that way there. So if you're sailing your yacht and you're in some kind of race or just trying to get along, stick around near somewhere between the clouds and the sink, and you'll get the best wind and the best performance. Now this is from Bay Winds. It's a chart at a particular time there, and it's showing the winds at right angles to the shore. If the sea breeze keeps building, it doesn't have to get much stronger than your 7 knots. It'll actually start to line up in one direction, and the right angles to the shore won't happen. In fact, if it gets more and more temperature difference between the land and the water, the wind will blow stronger and the direction will shift and become an ocean sea breeze based around Bass Strait rather than the bay. Lake breezes, I don't know how many in our audience are actually sailing in lakes at all, but a similar effect occurs in a lake, but it's very subject to the kind of land that's around the water. For example, if you've got a mountain range or high hills on one side, in the early morning, you will get sun shining on one side and the land heating on that side that's getting the sun. And in the afternoon, the sun has shifted across and the effect reverses. That will give you a breeze on one side, starting maybe 10:30, 11 o'clock, and on the other side, it won't develop until maybe 2 o'clock. So where you actually sail, if you're longitudinally on the lake, you sail up one side where the wind is and have to switch over to the other side because the heating of the land has shifted from one side to the other. In these cases, obstructions, valleys and funneling between the hills can have a huge influence on the wind. If you're going to sail competitively in these kind of areas, lakes, it pays to go and study the area for a couple of days beforehand. Now this is an ocean sea breeze. You've got much cloud over the land and the sink is further in here to the land. You've got more wind. For example, in Port Phillip, the wind reaches up to about 23 knots in a developed sea breeze on Port Phillip. And we get in the next slide, we've got how the sea breeze develops. It's cold over Bass Strait and warmer air on land, so the air comes in from the north. The sea breeze develops best when you've got calmish or light northerlies, because the northerly assists the flow in the upper atmosphere of the circulation. As it warms, the effect of the rising air over the warmer land and the colder air there, it starts first as a local sea breeze, and as it warms, it swings over to the ocean sea breeze. Now, the ocean sea breeze runs at right angles to the average shore, which in this case is across here. So we get a southwesterly sea breeze, but it starts in this kind of way. It starts here with sort of easterly, becomes a bit westerly, and then becomes the full-blown sea breeze with a southwesterly. And then, as the day keeps warming, the sea breeze, as the sun goes down a bit and the temperature difference gives away a bit, the sea breeze dies around about 4 o'clock in the afternoon. By 5 o'clock, it's noticeably different direction. And then as the heat goes out, the whole process shifts left. And as it dies, it becomes an easterly. As it dies, you pass into the realm of light wind in the sea breeze, and you need to look at your sails again, because there's no doubt that the set of the sails will have changed dramatically, and you're back into the car aft, car forward type thing. And the reverse process is the land breeze, which is very, very similar. The land is starting to cool, but there's been some warming in the sea. And so there's enough temperature difference between the sea, and the air starts to become relatively warmer, lighter, and rises over the sea, whereas the land has been cooling for some time, and sufficient temperature occurs for a circulation to start up, which gives you what's known as a land breeze. Now, the land breeze can be very important. I'm not 100% sure where today, you might know, Simon, but it used to be very particular around Werribee. And in fact, we used to do a lot of round the bay races at that time, and getting your boat into position to pick up the land breeze in the early morning was pretty important to get a march on your competitors. The land breeze doesn't start until about 1 a.m. in the morning, and it gives up about 9 a.m. It dies at about that time. It also only goes offshore for about 1.5 miles, maybe 2 in some places, but at least around the bay, 1 mile to 1.5 miles off the shore. So you need to get your boat close to the shore and keep an eye on what the depths are, of course. But the cold air is coming off the land and running out to sea in the circulation. The air that's coming off the land, you can smell it. You can smell fires, you can smell vegetation, you get noise carried in the wind, you can hear cars, sounds off the land, and the old saying therefore was, go into the shore till you hear the dogs barking, and then you know you're in the right position.
The really early good indication of land breezes is you can smell the you go from the sea smell to a land smell. We've just got one question from John Hanley, I think it is. John, do you want to ask a question?
Yeah, you might get to it. I was just when you're sailing on down the coast as opposed to Port Phillip, how wide's the area of dead air when you're at the border of the Seabreeze generally?
2 hours.
Sorry, distance-wise, I'm just thinking if I'm racing and I have to sail through that, approximately what sort of width would you would it be normally?
It's more a question of the development of the sea breeze, how it's going. What width you're going to cop depends on what speed you can make.
Right. Okay.
Got it? So the thing is, in coastal weather, we go into this a bit, but typically, let's say, sailing down to Tasmania, down the west coast, or running out to Port Fairy, somewhere like that, you position your boat close to the shore to pick up the very first of the sea breeze, and then as it develops, you can move out with it so that you don't get to where the air's coming down, the sink. If you're out to sea already, you have no chance except to suffer the sink. And even if you try and move inshore, you're going to have to go through the sink and battle through that. So positioning your boat while the process is happening becomes fairly important, and recognising the signs by the clouds on the shore tells you what's likely to happen. And we're talking about differences of 30 or 40 miles on a competitor.
Yep. Oh, thank you.
So that's a land breeze. That's right, a bit more.
Sorry, my hand's up. Can I just ask you to explain a little bit more about the sink, so that if I'm sailing from Brighton to Sandringham and we've got a local sea breeze, about how far offshore is the sink going to be, and what sort of range do I have where I'm going to be getting this sea breeze to be going further down to Beaumaris?
Your sea breeze will start close to the shore, assuming.
And where will the sink be? If I've got to tack a little bit, where will the sink be? How far out will that be from the shore?
In the winter time, in a local sea breeze, it'll be somewhere between 5 and 10 miles. If it's an ocean sea breeze, it will be around about 30 miles offshore. It will go there. But remember that the sink is, as the circulation builds and becomes stronger, the whole mechanism will stretch further and further out to sea with the temperature increase. As the day starts to cool, the whole system will start to collapse and become closer and closer to the shore. So the trick, if you can sort of gauge the temperature and so on, early in the morning, maybe 10 o'clock, 9 o'clock or something, you're in close to maybe 1.5 miles off the beach. And if you want to go offshore, you can move out as the day heats up, because the sink will be further offshore. But by about 2 o'clock, 3 o'clock, you'll want to be starting to move back in, because the sink will be moving from offshore towards the beach. You got that?
Yes, it's complicated to grasp, but yes, it's
Well, let me go back
to...
I'll go back just a little bit. This is the sink here. This is the heating of the land here. This circulation depends on the temperature difference between the land and the sea. The stronger the difference is, the greater range of temperature is, the stronger this circulation will become, and it will move out further and further. It goes over the land, the rise goes further into inland, and the sink moves further out over the water. And as it cools down, both of these contract again until the whole thing gives up. So positioning yourself not here, and that's over land, that doesn't bother you. Looking at this, you will see this because there's no cloud. Let me say, we see the cloud in the rise because of the condensation. Because the air is coming along here and going down, if you remember, the closer to the land you get, the pressure increases and the temperature increases as you go down. So you can actually, in a well-developed sea breeze, you can see the cloud coming up here and the cloud's moving in the top circulation, and gradually when you start to get near the sink, the clouds start to dissolve, and by the time you can't see any cloud, you're too close to the sink already. Does that help?
Very much so. Thank you.
Now, this is one of the biggest problems in sailing in land breezes. 1 a.m. in the morning or more, have a look at this guy. How much attention's he paying? If you're going to do light weather sailing, the hardest job is to get the crew to pay attention and look for any slight adjustments that you might need. Remember that the breeze strength is not very high, and all that business of the twist in your sails is critical. Devise ways to keep them awake or something. Hand out a lolly or something like that. Have a few jokes, anything that'll keep them awake and paying attention. And then we have a process called catabatics. And the top of the hills around the water surface is already colder because of the height. And as the night comes on, the land keeps on cooling, so much so that the difference in density between the cold air on the mountain top becomes very, very cold, becomes very, very dense. What it actually does is start to slide down the side of the mountain or the hills. And would you believe our Yarra Valley at the top of the bay is just such a place. The hills through the gap, Mount Macedon, etc., the air cools there, so much so that it drops into the Yarra Valley. They've got a place called Coldstream there, and there's a reason for that. So as the cold air drops into the valley, it starts to flow like a river. And it comes out at Williamstown, in our case, and runs out to sea. And if you're ever dreaming of a Melbourne Hobart or something like that, learning this stuff and putting it into practice is critical. Katabatics don't run very far out to sea. It's a similar thing. 3-5 miles is a long way for a katabatic. Generally, like a land breeze, they're 2 or 1.5 miles offshore. The exceptional case is in Antarctica. When they get blizzards of 100 knots, they're actually katabatics coming off Mount Erebus down in Antarctica. The Bora Bora that runs out of Croatia, that's another katabatic. It takes 2 or 3 days running along the land from the Arctic Russian cold areas. Sorry about this. I did too much talking through the afternoon. Anyway, the Yarra Valley is one. You can see, particularly around autumn or early summer, spring, you can get a forecast of, say, 30 knots or something around Williamstown, down across Brighton, and you can have a look and say, well, that's it, that's the end of sailing today, something like that. And by 9 a.m, the wind dies and it drops out to a lovely 10 to 15 degree day. I don't know if you've ever seen that there, but it certainly happens. And this is a picture showing the Yarra River, the hills, and this is the valley that runs down and through here where the cold air runs. Now the air, as it drops down, it warms and it expands and becomes lighter, but at the same time, it's hugging the ground and losing heat, so the process continues. But they're race-winning moves to pick a katabatic correctly. In the Melbourne Hobart, for example, you can get a 70-mile jump overnight on a competitor if you can get in the right spot. Any questions on this?
There's nothing at the moment, but just give them a few moments to
Think about it.
Yeah, it's interesting. If you look on the bay, the katabatic that comes down the bay can roar at 15 to 20 knots, and it can stop by the time it gets to Fawkner Beacon.
Okay, we'll move on.
Yeah.
Going down to Tasmania, and there we've got the Derwent Valley, which runs down between the mountains and so on, further inwards into inland Tassie. This is a sped up diagram, but here you can see the cold air running down the valley in this katabatic. Just have a look, cloud formations, sky, the hills on the side. This has got a particular name. It's such a common phenomenon. It's called the Bridgewater Jerry.
So that completely stops as soon as it's 8 o'clock at night. Is that right? After Christmas?
Don't know about that. You actually get the sea breeze up until about 11 p.m. and the katabatic starts about somewhere around 11 p.m. or thereabouts. You see the day's warmed up and it's changed. Now, I'm going to run this again, and I want you to see if you observed stratus cloud, altostratus cloud, stratocumulus cloud, cumulus cloud, an atmospheric inversion, laminar flow, waveform cloud, and orographic lifting. So I'll run it again, see what you can see. Here we've got stratus. This is stratus. Sorry, there's an inversion here, holding cold air aloft, stopping this from rising. There's orographic lifting. Right, that's the air piling up against the hills, being forced upwards. And that's also happening over the hills here. This is breaking up into waveform cloud. Here's our waveform cloud up here. Here's the orographic lifting. And the temperature is starting to warm up and the air is mixing here. And the stratus on the land is disappearing. We've still got the orographic lifting, and it's starting to become a bit of a temperature-driven cloud, looking, it's altocumulus starting up there. So every one of those different types of cloud is telling you something about what's happening where you're sailing in such an area. And whenever they have a regatta down in the Derwent Valley, down there, the locals always come out on top because they understand all this down there. Okay, let's have a look at obstructions. And I've got here Arthur's Seat down at Dramana. Very often in our events or sailing, we're coming along the South Channel, along this way, and we see the wind change. What's actually happening? Well, air is just another fluid and it behaves as a liquid in turbulent flow. So there's eddies in the atmosphere and so on. If you think, one of the best things you can do is have yourself some little pieces of stone or something that resemble a hill or some kind of wall or something like that. And on a rainy day, when there's a stream of water running down the road gutter, drop your little models into the gutter and watch how the water behaves on your model, because exactly the same thing happens with the air out on the water. And let's say air is actually heavy. It's surprising just how heavy it is. A 1 kilometre long parcel of air, a half a kilometre wide and only 10 metres thick. That blanket of air weighs 6,000 tonnes at sea level and 20 degrees C. If you want to put 6,000 tonnes up over a hill, how much energy or force do you need to get that to happen? So the lesson in this is that wherever it's got a chance, air will always go around an obstruction rather than lift over the top. And when you're coming to hills and coastal cliffs, all that sort of thing, try to think of it in that way and work out what might actually happen. And the other thing with this is as it tries to go around, surface friction is there where the air is running around or over the land. So whatever there is on the land that can give increased friction will make a difference to the speed of the wind that's happening in that area and the amount of turn, right? The Coriolis force will turn the wind when it stops for some reason or slows, and it will veer. And I suppose you've gone past Arthur's Seat and into the Dramana Bay there and felt the wind changes as you go around it. There's a bit of a diagram, and this in particular is a hill. It's showing the roughness on the surface of the hill that can be slowing the wind and having an effect. A bulge here on the land. Now this is actually a diagram of Cape Otway. Now what happens, especially in laminar flow, that is wind not much more than 6 knots blowing on shore, and it's smoothly running onto the shore. As the air comes in, it it can't lift over it. It will try to go round, but where it's forced to go up and over, it will pack up calm air or stationary air in a bit like this, and then it will lift over that calm air and continue on its way over the hill. As the wind increases, you start to get a calm air patch here, or you get a rotor, and that is the air's coming this way and going around like this. It is possible in this area to have 2 boats sailing along the shore a mile apart, both tacking in both on opposite tacks, but going in the same direction because of this rotor, right? The wind's going that way or that way, coming up to it. Rather tricky. The same with the wind coming off the shore. The amount of roughness along here is the amount the wind will turn and come off the hill in a different direction, and more likely you get a skip across here. You get a dead patch of air, and if you get your yacht in here, you will sit there while the others all go around you. This is turbulent flow by the time this happens. If you look at the top of the hill, you get orographic lifting coming up the side of the hill and making a capped cloud where it reaches condensation level. As the wind speed increases, the top here starts to form cumulus cloud, and you get waves coming off the top. You can see them in the distance. So looking at the clouds in a situation like this tells you what's likely to happen, whether there's a rotor or a dead patch there. Race winning things. And when I talk about racing, I mean also if you're cruising or pleasure sailing, getting to where you're going is all the fun of the process. This is running along the channel to Geelong, having come through, come off the bay and running along the channel into Geelong. There are little rises and hollows in the land when you look on the shore. The wind will not go over if it can avoid it. It will run along or around and come out in a dip off here. If you've got a wind blowing off the shore, you might see the savvy sailors, they move in and out on the channel to get the best winds. So need to be conscious of that sort of stuff. You're not going to pick this all up in a month or two. I keep saying 3 years before the penny starts to drop properly. Now, coming back to Coriolis and the gradient wind aloft, and just repeating there, when the wind is slowed, it turns clockwise. That is here, it veers and comes down here. Here's off St Kilda and Brighton. If you've got a southerly wind blowing and you're sailing along the shore, what's going to happen here? Well, the wind that's blowing over the land, over the rough land, it gets slowed on the land. If it's buildings, it gets slowed very significantly. If it's shrub or something like that, it still veers. It just depends on the surface roughness. But the wind turns round and goes back over the shore. But the wind offshore is following the gradient direction. So if you get one that way and one that way, what do you think is going to happen here? The answer to that is a lot less than what's happening here. So this is what's called divergence. And if the wind's a bit strong and you don't want to change sail, for example, you go into the shore and you can still be going with a good breeze, but you don't have to change the sail because the wind pressure's a fair bit less. It's usually a reverse case, you want more wind, but anyway. And if you've got a northerly running down the shore here, we've got the wind going over the land, being veered and coming out this way. And the wind over the water is following the gradient wind there. So you've actually got, if you remember in the vector examples in the first session, when you get a convergence, the wind strength here adds a component into this here. So you get a much stronger wind in this case. Now we've got a bit of an exercise. There must be plenty of people here who've come in through the heads or from down the bottom of the bay there, and you come in along the West Channel or on your way to Geelong, and you come along here on your way. Have you noticed a change as you come along here and the wind moving around a bit? What's actually happening? This is our wind direction in a sea breeze. Here is our yacht sailing. They've got the Prince George pile marker up here a mile or two past the shore. And the question becomes, what's going to happen? So here's your exercise. What happens at Prince George Bank Beacon? Simon, you've had a poll on this?
No, I don't have a poll for that. We'll just get them to text in their answers.
Okay.
You mean put it into the chat, don't you, Simon?
Yeah. Sorry,
Yep.
put it in the chat.
Thank you. Do you want to go back to the image, Robin?
Yeah, there we go. You're proceeding along here and you're heading up the bay towards Melbourne or on your way to Geelong, something like that. And Prince George Bank is here, or Pile Marker it is, whatever it is here. So this is the Seabreeze. What's happening to the wind as we move along here?
We've got one answer that it strengthens and shifts west.
Shifts.
Then we've got one that says that they're slowing and veer. It'll veer and strengthen as the breeze from Coral Bay mixes. And another one says it'll strengthen from the south. We've got wind winds back to the west. We've got someone saying it's becoming more southwesterly. And Tony's saying it'll increase and veer north. Okay, Robin, do you want to maybe run us through what the answer is?
Yes, we'll talk about it. That's where the lesson is. When you're adjacent to the headland here, I think it's yes, we get the wind veering off the headland, and then it combines with the sea breeze. You get a convergence here, and the wind veers. And then as we move up alongside here, the veered wind off the headland combines with a gradient southerly wind to become south-southwesterly and stronger. And then as we get past the headland, we lose the component of the veered wind off the land, and the wind actually moves back again towards the southerly, moves back up from the southerly. You all happy with that? Can you see the application?
Does everyone understand that, or does it need to be
Yep.
gone through again? Okay, no hands up there, Robin, so move on.
That's pretty good, isn't it? We're doing well. Well, everyone's doing well. Now we get into around Carrum, and I think you had a race down to Blairgowrie just recently. And yes,
Yep.
right. Well, this is partly about that. The Carrum Bight has a notorious reputation. Positioning your boat, how far offshore, where you're going here, is usually fairly critical. So what actually happens here? You've got hills down here, Oliver's Hill, and so on down there, but they're really far away. They're too far away from the Carrum Bight to make any real difference. We have it's repeating there. We have the wind over the southerly wind over the land here, which has veered. It turns round and heads inshore. Wind keeps going across here. The inshore component here will gradually disappear as you move offshore, and there's a magic spot somewhere along here where you get the best of both worlds. We've got the veered wind here, and we've got the local gradient wind here. So we've got a zone of divergence in this area here. That is, there's a hole in the wind here. And this zone of divergence will mean that anybody who's stuck in that will miss out compared to anyone who's in a position just far enough offshore that they're not getting that influence and getting the best wind. Also, you will have noticed when you're tacking along a shore such as this, you get one better tack, but as you go in on the tack, you bend more and more and more. And then when you move away again, you go good tack, and gradually you lose it again. So the positioning and understanding what's happening is fairly important. A little bit of a break, yes?
Yep. So we're 8:22. So we're a bit slow at the moment. So we'll come back at past. So we'll have an 8-minute break. Any questions while we're waiting? We can happily answer those.
Plenty to think about there, I think.
Yep, there is.
How are we going, Simon? My watch, my time
Yeah,
says.
got 3 minutes more, or 2.5 minutes more.
Right.
Tony Foss, you've got a question. If you want to take yourself off mute and ask.
No, I was just back early, Delma.
Excellent. We'll leave your hand up. And so all those that are actually back, just pop your hand back up so that we get a bit of a sense of how many are back. Okay, we're about halfway back. So if you've just rejoined, just pop your hand up so that we know that you're back. So if anybody's just come back since I last announced, just pop your hand up when you get back to here, please. One minute to go. Robin?
Hey.
Okay, if you've come back and not popped your hand up, just pop your hand up to let us know you're back, please. Great. So leave your hand up so that I know that you're back. I'll pop it down at the end. Okay. Robin, I think we're pretty good now. So if you want to kick off and everyone either pop your hand down or I'll go through and do that. Thank you.
Okay, this is a phenomenon in Port Phillip Bay where Coriolis has a lovely time. It's called the Spillane Eddy. It happens in autumn, and if you've ever seen the smog on the bay as a sort of a orangey brown cloud, in a light northerly, over 2 or 3 days, this smog cloud drifts down towards the bottom of the bay, and later in the day, when there's a little bit of sunshine come around, a local sea breeze starts blowing from the south and blows the smog patch back again. And then as it dies, the northerly floats back in, and the end result is for about anything up to a week, this smog patch builds up more and more and more and just goes round and round and round. So the Coriolis has a field day there. And then on the website, this is for observations if you're in around the bay race, or perhaps you're assisting on a race management boat. These are some of the things you can look for that help. The actual wind on the water, if you look at the Beaufort scale on that, you can tell the strength of the wind and where the disturbance on the water is. Watch all the boats that are going the wrong way. You can look at the clouds because you can see what's developing there, while some sailors are not looking at the sky, and you can see who's doing what's wrong. The same as smoke out of smokestacks and other boats under sail or anchor, which way they are hanging on the anchor. And you can go to sites like Bay Winds or the Bureau's station observations. During the winter series, quite often we'd be looking at the wind at Point Wilson or South Channel and looking at what is coming up the bay by plotting these various positions, so you know how to manage the race. And if you're in a yacht, of course, you can work out what's coming. With the observations, this is a cold front going through South Channel Island. You can see the wind there, and then suddenly the front goes past and gradually diminishes. It didn't want to go, but it went.
Can you see a little bar down the bottom that you can push, Robin, a starter bar?
Bar.
Just down the bottom might have a little triangle start bar or something.
No, can't see that.
Okay, we'll just move on. We'll do that later.
Yeah, I tried it this afternoon. It was working.
Okay, we'll go back one slide and try it once more time.
I did that.
No. Right, keep moving.
That pause thing up there wouldn't have anything to do with it, would it?
No.
No. Okay, this was about predict wind and what was available. We'll come back to it. A bit about tides. The main forces that cause the tides, the pull of the moon and the sun, and the predominant feature is from the moon. And currents are subject, they're a bit similar to the wind and obstructions and so on. We'll get into some explanation.
Tides, the up and down movement of the oceans, are a result of three main forces: the influence of the moon, of the sun, and the rotation of the Earth. The Earth and the moon are mutually attracted by a gravitational pull. But inevitably, the point on the Earth furthest from the moon is less drawn than the point closest to it. Thus, the gravitational force has an effect of stretching the Earth, causing the sphere to deform and the waters of the oceans to produce twin tidal bulges, or static tides. The effect of the sun is the same, but because of its considerably greater distance from the Earth, the influence is only half as great as that of the moon. If the Earth, moon, and the sun are in alignment, the effects are multiplied, and it is then at the highest tides, the spring tides, occur. But if the Earth, sun, and the moon are at right angles, their effects counter each other and produce the low neap tides. All this is, however, influenced by the rotation of the Earth, whose main effect is on the time and place the tides occur. Thus, waves form on the ocean surface of varying heights. The currents, depth, and the shape of the coastline will also determine the power of the waves, which helps to explain why tides are usually semi-diurnal, with 2 high waters and 2 low waters a day, while in some places there is just the one daily tidal cycle.
Just to repeat that again to show when the sun and the moon are aligned, they add to each other with gravitational force, and when they're at right angles, we get what's known as a neap tide, where you get nowhere near as high a tide. Looking for tidal information, you remember the boxes on the bomb site? They have one of those boxes that have tidal tables. And typically they produce a table like this, which give you the days for a month or something. If you look, I can't quite see it here, but if you look on the website, you'll see a little piece somewhere up here that says more information. If you click on the more information, you can select the table up to 2 years in advance, and it gives you a whole range of other places, not necessarily Melbourne. That's where you get, like down in Tassie and Queensland and so on like that. You can get all that information. Note in the table, you've got a full moon here. Not a full moon, I mean it's on the opposite side. You've got the 2 in alignment, the circle here, and you get the neap tides shown here. So you can get a pretty good idea of where it is, where the tides are, I mean. One of the other things to look for is if you look at the range of tide, see it's 0.36 meters here, whereas down here we've got 0.77 meters. So that's obviously building up towards a higher tide. And when you're looking at the currents and so on, the currents in strength move with these tidal ranges. You get the same sort of effect. You would think that might be logical, isn't it? Why is tide direction and speed important? Well, obviously, if you're battling against the tide in a race, it can mean a lot. It can affect the sea conditions where you are, and it can affect the type of a ride you're actually getting. How do we tell on a yacht what the tide direction and strength is? Well, number one, you can check the drift with a transit. That'll tell you whether you've got a cross tide. Here we've got two markers, and you look, it could be trees on the shore or something like that, a marker and a tree. You line them up and you watch. If they stay in line, then you don't have any cross tide. But if one or the other is shifting sideways, then that's a sure sign that you've got a cross tide. Lost my pointer here by a little bit. That's better. If you can put an object floating in the water, and as you move along, you can see where it's actually going. Or if you're in a race or something like that and you're hovering around the start boat, you can put a little piece of paper in the water and watch where it's going in relation to the race boat or yourself not moving to get an idea. Looking at the wake of your vessel when you're steering a straight line is the tide pulling the wake over, or pulling the boat from right to left in this case. And you can see the bend there allows you to make some adjustments. When you get down the bottom of the bay along the South Channel and areas like that, it becomes pretty important in making good time. Okay, thought I was looking at the same picture twice. In the southern hemisphere and our mid-latitudes, Coriolis works with the tide as well, but land effects can be a bigger factor. And generally speaking, in the southern hemisphere, if you face the direction of the tidal flow, the stream will tend to be on your left, which is why we get the circulation in the bay is clockwise. Even though it's not very strong on the western side. Heavy rain, you can see here the Yarra stream. You can see the Yarra water, the muddy Yarra water coming down. It's coming down, fanning out around here and then moving on down. Thinking about the Coriolis effect, it takes a bit of looking at it and thinking about what's actually happening to understand that. But certainly the stream on your left, when you look in the direction of tidal flow, works out. There's a lot of factors, and I've got a couple of examples here as to where the tide flows and some exceptions. But the important thing is that the tide turns first in shallow water or on the edges of a current. Now that means in deep water, the momentum of the current will push against a changing tide for a while. So maybe up to 20 minutes past the forecast change of tide, the edge or the center of a channel may give you the opposite direction. Starting a race down at the South Channel, say from Portsea, getting in the right position out into the channel or out into the shallower water on the edge of the channel can make anything up to 10 minutes difference. And here's another bit of the Yarra and the tide, what happens at the top end of the Yarra. Here you get some of the little currents that flow up in the top there, particularly if you're racing out of Hobson's Bay, St Kilda or Royals in their events. You can position your boat here watching where the tides are and where you get slowed or where you can pick up a little lift. And here's the general effect. They're either zero or very light current strength coming from the west, curling around at the top of the bay. 0.75 or more down past St Kilda and Brighton is quite common there. I actually had a diver down cleaning my boat and said to him, "How are you going to go? The water's as muddy as anything." And he said, "I'm 5 and 6 feet under the water and it's as clear as a bell." So the salinity in the fresh water was making a difference in the positioning of the height of the water there. That's another picture of the silt and mud coming out. You can just about see the circulation here and the West Channel, South Channel, where it is there. And this is the shipping channel coming down and the bottom and the depths. It's one of your pictures, Simon, is it?
Yes, so that's a picture from Navionics.
Navionics, right.
Navionics, right. And so you can see down the bottom, it shows you where the tide is. And this is just showing you the tide or the state of the tide with Navionics.
Right.
Right.
Very useful.
And so it tells you that, the times and everything.
So you can get all these bits of information, probably sailing down the bay or any enclosed waters. The tidal stream's momentum, as I said, the momentum continues in deep water when the tide turns. But if that's against you, you stick to the edges and you get a lift for a good half hour or so. And at the heads, slack water's not at the change of tidal height at the heads, but 3 hours after the change. And therefore, it's important to get the information off the tide tables as to when it's slack water. And if you've done any offshore events with ORCV, we start 20 minutes or so before the predicted tidal change so that we're out as to where the sea conditions change by the time the actual change occurs. And that's an example of the slack water, the tide changes at the rip. So they've got different colours for ebb and flood, and they've got the time and they've got the maximum flow rates for each and the time for those. So you wouldn't want to be going in or out of the heads or something without having some tables. But it is also in entering the heads, you can come in any time at flood tide. That won't be a problem. And there are tides along the South Channel and in the West Channel. They're up around 1.5 knots quite often and 2 knots down the channels. And the rule of 12ths has everyone done the rule of 12ths yet? I think we teach it somewhere, don't we, Simon?
Yes, it was in the navigation course.
Okay, that's good. Okay, well, once you get out the West Channel or down the South Channel and you get to the Hovel, the tide dissipates very, very quickly. But the interesting thing is if you're going to Geelong, it gets up to 1.5 knots maximum at Point Henry where it narrows. And a friend of mine who's a ship's pilot said he was running late one day and he steamed through the Point Henry narrows there at as fast as he was permitted. And he said the sea level dropped that was nearly 3 feet behind the ship. Just an interesting little snippet. This is Western Port, and although I said the circulation goes clockwise, and it does here, when you get up to Sydney, it's very, very different. And the reason it tends to flow out a lot here is because of all the streams that flow into Western Port from the lowlands there. Typical tide diagram showing the high tide and low tide. Various programs arrange the information differently. If we look at Sydney has got very deep water channels and some shallows. So whether the tide's ebbing or flooding, it tends to stick to the main channels. And in South Australia, it's a very complex situation because I think Kangaroo Island alters the external aspects and their tidal predictions are only good for about a week at a time. It changes so much according to the weather and so on. And that's the rule of 12, so it's in your notes once again there. This is an extremely useful thing because current flows and everything all follow the same kind of pattern. And this is showing the Derwent Valley, or this is Storm Bay actually, from the Derwent River. It's showing a typical flow as the tide changes and the water comes out of the river. Got a better diagram somewhere there. But you see this rush of water that comes out is approximately 1 hour after low tide. And I think that would be pretty general in a lot of those situations. So the technology which you can use, and perhaps wind predictions, these would be the major things. I don't know if I've got it there a bit later, but windy, when you get to the windy site, windy.com, there's a piece there that says more layers in the selections down the side. Make sure you press on that and have a look. There are huge numbers of selections there. They give you almost anything and everything. You can work out when it's raining. They give you diagrams of clouds across the water and so on. It's very comprehensive, and Windy is a site in development still. Although I can pick a few faults with it, I think they're improving all the time, and I don't expect them to be a problem for much. Some of the models, the codes that are there, this is the subject matter we've been going through, but the some of the models that are there, weather zone, Tide Tech will sell you tidal information for a particular event. Bay Wind gives you locations that you can use for various places about the wind. And Predict Wind is very valuable offshore and so on. And now that they've got the access model, they've got 3 models that they're using now, is very good. I hope to have an example here to show you Predict Wind, but it refused to cooperate for some reason.
There is a picture later, Robin, in another slide. If you go further on, you'll see slides of explaining them.
Okay, what to remember is you can get all sorts of information from the internet, but there are many, many things that it doesn't give you. And because we're interested in a short distance around the boat, we want to know what's happening 1 or 2 kilometres in front of us and around us. Keeping your eyes open, looking at the clouds, the sea conditions, everything you can get is helps a lot. Speckles, we did all that.
Yeah, just keep moving, Robin. It adds bits as you go along.
Oh, okay. Weather maps there, different weather maps. I think this shows, does it?
Yeah, just keep pushing. It shows you where you're going.
The interactive weather and wave forecast notes have a lot of selections in them also, and it's very useful to play with all that sort of information. You can predict rainfall and all sorts of things.
Yeah, if you keep clicking, Robin, it'll show you what happens next.
Yes, surface pressure and rainfall. There's a huge selection of stuff up here.
And it'll show you that there, Robin.
Yes, very good.
So particularly if you're looking at surface winds.
Yes, surface winds from different models. It's important every time you change something or a selection up here, it's necessary to click refresh view or it'll stay on the map you had before. This was about comparing the different maps showing the area, inland waters. We were looking at this area. So we've got the isobars here. We've got the wind arrows here. And compare the two, the spacing there, and how you work out the wind directions from the isobars. You can study this and imagine what is actually happening here in order to arrive at the wind directions here. And an exercise you can do yourself at any time is to look at a map and go through those various displays and try to assemble your own forecast like this, and then to look at the forecast or look in the next couple of days and see how you went and what you get. That teaches you an enormous amount about getting it. And this is a predict wind color chart. You see he's got the vectors, the small vectors there depicting the direction of the wind. Once again, you can compare that and see the systems and how they're crossing the isobars to get the direction.
And click again, we'll put the isobar map on top.
I can't quite read it, Simon, that's the trouble.
Yeah. So isobar, just click, do another click, and it'll put the isobar on top. And so there you can see the isobars and then the wind arrows. And then click again.
So we get the table of the values of the wind arrows, and you can look at the color, at the code for the different wind strengths, and you'll see the half a knot, 50 knots, for example, and the combination of all of them. A lot of maps have this kind of information displayed. Now, this is the windy map. You'll see here where is he? More layers. Oh, here's the more layers. If you click on more layers, you will actually get a string of different selections right the way down here. And I think they're down about here now, aren't they, Simon?
Yeah. It's changed a bit since we put the slide up.
Yeah.
But this windy site, if you haven't seen it, you can spend days looking at the various things they put on top of here, and you can get all sorts of things that you can put on top of here. And they've really specialized themselves for sailors and for airplanes and flyers and paragliders and all those things. And you'd find most sailors find this a very useful feature. If you're planning a journey from A to B just down the bay, you can play the timeline down the bottom, and it works quite well. So it's a bit different to the other services you find, but you can play it down the bottom and you can get a good sense of what happens.
Right, and the other thing is it's a 10-day selection, and once you get the hang of isobars and so on, you can move out to 10 days and look at the isobars a bit further on and get a very rough idea of what it might be coming after the 10 days. But it's getting a bit dodgy after 10 days, that's for sure. But professionally, you can have a service that'll give you up to 20 days, but I don't know how good that would be. And that's about as far as we go.
All right, thanks very much, Robin. We've got a question from David. If you'd like to ask your question, David.
Just going back to windy on the slide that you showed before, what's the resolution? If we're sailing in Port Phillip Bay, can you enlarge that so you can see when we're going past Arthur's Seat or when we're going to Port Islington, the difference in the winds?
Yep, we can do that.
You've got zoom in and out up here, but somewhere there's a plus and a minus, I fancy.
Yeah, right.
If you're interested in a particular position, you can click on that position and it puts up this mast and flag showing you the conditions, and it will maintain that position. For example, if you play the time scale along here, it will change this as the that moves along.
Share my screen, which has got a live version on it to show them.
And is this smart enough to include convergence and divergence that you were discussing before to give you the overall wind, or is this just the...
Yeah, no, it gives you the overall wind, and so it's their best judgment. And you can see now down the bottom here where my mouse is, they used to just have two models, but they now have another two models, access and icon. And if you just play it, now you can see it going across the day. So
did you want me to share that screen?
You
can control it.
Yeah, I'm doing it.
Yeah,
the
right.
White lines that come across us are the isobars. And I always just use this so we can go in and out, and we can see the isobars coming across. And so you can see it playing. And so we're going up north. So I'm watching this low pressure here. And so I watch that over the days and see what happens if the low pressure is going to come down too close or not and have too stronger winds. And then I'm watching this low come behind us. And so that's how you plan longer voyages. But if you're just going around the bay in your zoom, and you can see the winds as they change. And you can see by the colours of the winds here, they're talking about the different pressures and things that happen as you go through the system. All right, is there any other questions?
We've got a question from Dean. Do you prefer windy or predict wind?
Dean, I use windy for quick planning, and I use predict wind for precise planning. So if I was going to voyage, and so like we're taking summer's lease to Sydney, to Hamilton Island, we will always make sure that I use windy for the final preparations. But if you don't want to pay any money, the windy product is very good.
Thank you.
Are there any other questions?
Sorry, Simon, did you mean for that plan you'd use predict wind or windy? Sorry.
So this currently I've got up
Yep.
is windy.
Yep.
And I'll show you predict wind, and I'll give you an example of what we're doing. So there's my plan to go to Eden, and I just download the model.
Simon, I think you used the words that you used windy for the final.
Windy
predict wind for the final, don't you?
Windy here for my guidance plan, and then I go to this model here, and you can see it's showing me the wind, and so I'll choose the model that I trust here, which is PWE, and I've set the start time and everything to go, and we'll just wait till it develops, and then you can see basically it follows the path. So I've got the wind behind me looking quite good, softens off a bit by around the bottom there, and then it comes in a bit harder, but still okay. The direction a little bit on the nose there, but shouldn't be too bad. It's light, and then it'll show me as I go across a bit more on the nose, so maybe not such a good time to go, but we'll watch it as it comes along, and it will go
You'll
up.
Be motoring in that anyway.
Yeah, motoring a bit there. And then if you look at the routing, if I go back to here and I go to the tables and I go to the summary. Come on, yeah, there's the summary. So it tells me it's going to take 2 days to get there. It's 340 miles, and it tells me the average speed that I'm going to be going to, the passage time, the motoring time. So it tells me how long I'm going to be motoring for. And then the bit that I like particularly, it tells me the time upwind, it tells me the time reaching, and up here are the models that they have. One of the easy ways of this thing to see is what the times are like, and if the times are similar, you know that the models are similar. So there's the two products that I use, but to get this service here that we're using, this takes a subscription. And it's about $90 for 3 months, I think is what it is, roughly. And then the other thing that you can do is quite useful. It's got a daily briefing thing, so it tells you what the wind is in the morning and the evening. And if we want to look at Friday, we can look at what tomorrow is. So It's 4 degrees low, 3 to 7 knots, so quite a nice, comfortable day. And if we look at Saturday, any of you coming out sailing, we've got northerly winds. So in the morning, 9 to 13 knots, so 10 knots. And it's going to be 15 degrees, so a lovely day for sailing on Saturday if you're joining us.
Okay, any more questions? Otherwise, we're going to call it a night. It's 9 minutes past 9. So, looks like there's no questions. Can I get one to give Robin a quick thank you, please?
Yeah, big claps there. Go to the reactions and give Robin a nice clap if you feel that way. I'll give him some hearts. Clap.
Thanks, Robin. That was great.
Okay.
Okay, good. Sorry, my voice was giving out a bit.
You came good in the end, Robin.
Yes.
Okay, thanks everyone for attending tonight, and we look forward to seeing you at the next race down in Geelong or the next course that we do.